I'm Thomas Birner today. He's from the Department of Atmospheric Sciences of Colorado State University in Fort Collins. This is where my PhD advisor was getting his PhD. Long ago in Israel. Now Thomas got his skipped BA actually, MA in physics from Leipzig. He's one of the people who came from eastern Germany. So he's from the same side of the iron curtain. After that, he went to do his PhD in atmospheric science at the University of Munich. And after that, he spent some time doing postdoc in two different places. First, it was in Reading in UK and in University of Toronto. After that, he moved to Colorado State, where he is now a professor, and he's working on very interesting things. Actually, he's working on things quite unique. I didn't see many other atmospheric scientists doing so. It will be very interesting, and we shall see what he has to tell us. We had a lot of physics this week, and I think this will also match with other physics seminars which were given so far and will be given later with other visits. So, please start.
Thank you, Boris. Thanks for inviting me. Thanks for the introduction. If you follow my path, I'm moving on the Great Circle. So if you want to know where I'm moving, I don't know. Maybe I just stay there. I'm in the atmospheric science department, and I'm an atmospheric scientist. So I'm going to try to not use too much jargon. I know most people here are more on the ocean side, but if I end up using something that's unclear, please just go ahead and interrupt me at any point in my talk. I think this is general enough, though. I think this is just very basic jet dynamics. In my case, this is an example from atmospheric science. So there's a pretty picture of the jet stream there that I found on the web. I didn't produce it myself. But last night I took a picture of my hotel room that was up on the wall there, and it reminded me on jet streams in the atmosphere and waves on the jet. So there you go. I think you can even see me take the picture there. There's a little bit of a mirror there.
That was very accommodating.
Yeah, I wondered, did you go ahead and put that up there for me, or I don't know. So here's sort of an overview of the region that we're going to talk about. We're going to talk about the subtropical jet stream in the atmosphere. So here's a latitude, height picture of the atmosphere with lots of things in it. I won't really explain all, but this is from a review paper. Those black contours here are the jet stream, the wind contours. So you got a jet close to about 10 kilometers altitude. That's the subtropical jet. So that's what we're going to mostly focus on. It ties into a lot of different things in the atmosphere. Well, first of all, those are the strongest winds, at least in the lower part of the atmosphere. They're there. You connect the tropics and extratropics to the subtropical jet. Those wiggly arrows there, those are supposed to be Rossby waves and can propagate across there, and they can induce mixing between the tropics and the subtropics, so that the jet is important for that. It also sits as sort of the boundary between the troposphere and the stratosphere aloft. Here's your stratospheric circulation. So it connects a whole lot of different places in the atmosphere, sort of important from that perspective. Here's a different picture of climatology. If you look on the left, the contours are the wind speed again. So this is zonal mean, zonal wind in the atmosphere, 10, 20, 30, 40 meters per second there in the core of the jet stream. This is for northern winter. You'd have it at a different place and weaker in northern summer. We see where it's located. It's about 200 millibars in pressure. And then there's some other things on there. I got isentropic surfaces, the isopycnals of the atmosphere. There are these dashed lines there. So cold is down there. It gets warmer as you go up. And you also see that you can connect troposphere and stratosphere in some of these isentropic surfaces. I highlighted this 350 K surface. That region is going to come up more later in the talk. So this is roughly at this 200 hectopascal level, 12 kilometer altitude. And so you've got this dashed line, and it's almost horizontal in this case. And again, you're sort of connecting tropics and extratropics here. And isentropic surfaces are important because for adiabatic processes, potential temperature is conserved, so you would, in those processes, you would stay along those surfaces. So if you have a Rossby wave propagating along, and if it's adiabatic, it would like stay on one of these surfaces. So that's why they are important. They're sort of quasi-horizontal. Well, that was on there. The blue lines are potential vorticity contours. And the main thing that you can see there is that they're tightly packed in this layer. I didn't draw all of them on there, but they are much more tightly packed in this region there. This is the tropopause, and in this way the tropopause distinguishes air that has low PV from air that has high PV, which is the stratosphere. And so if you cut through on one of these isentropic surfaces, you find there's a huge gradient across the tropopause in potential vorticity. And again, that's important because PV is also conserved for adiabatic flow. So in order to go from the troposphere into the stratosphere, you have to change your PV somehow. And you don't have to just change it a little bit, you have to change it by a whole lot to do that. So in that sense, the tropopause is like a mixing barrier because you have vastly different PV on either side, even though you can move on the same isentropic surface there. And you see that a lot of that gradient sits right at the subtropical jet. In fact, my color shading in the background quantifies the strength of this Mayer-Jonal gradient in potential vorticity. You see that it maximizes right here, just a little bit poleward of the subtropical jet core. So far, so good. So what I'm going to use a lot in this talk is, because of the dynamical importance of the surfaces that I just introduced, the potential temperature surfaces, I'm going to work in that coordinate framework, in the coordinate framework of potential temperature. So on the right, you've got the exact same data, basically the exact same plot. It's just the vertical coordinate is now potential temperature as opposed to pressure on the left. And so the dashed contours on the right are pressure contours now. And again, you can see that here's 350 Kelvin. This is roughly at the 200 hectopascal pressure surface. And everything looks a little bit different, especially down here. You can see, those isentropic surfaces, they tilt up toward the pole, and that's why the pressure surfaces here tilt down toward the pole. Right? So everything is consistent there. Your subtropical jet, I should use the pointer more. Here's your subtropical jet. So let me just sort of motivate by running an animation why PV on an isentropic surface is useful. So this is going to run through an entire cold season, northern hemisphere cold season, starting the 1st of October, runs all the way through end of April. And the colors are proportional to potential vorticity, and all you need to know is that blue is small and red is large. And I picked a specific value. This is the black line, which corresponds to the tropopause on this specific isentropic surface, right? So if I go back quickly here, it's this 350 Kelvin isentropic surface. So you're on the troposphere here, and then you're in the stratosphere. For the poleward, that's what you can see on this surface with the red and the blue. So let me just run this. And you can hopefully see how a lot of the dynamics, especially the wave dynamics, is really well described by a field like that. All you need to do is just focus on that black line, and what you end up seeing is Rossby waves amplifying and decaying along the tropopause. And they're really amplified at the tropopause because potential vorticity represents the restoring mechanism for Rossby waves, and there's a strong PV gradient across the tropopause, so that's why they're so visible there. And then you can see several things that they amplify. You get wave breaking every once in a while. I can try to catch one of those. Let's see. Here's an example where you have a wave breaking phenomenon happening right here, where there's sort of overturning of contours, and you got high PV, equator order of low PV, and then high PV again. So this is sort of a wave-breaking phenomenon. But you can see that this is really going on all the time. And a lot of the dynamics happens right there at the tropopause. So this is also where your subtropical jet is. And so really what this talks about is about the dynamics of these Rossby waves that are on the subtropical jet. You can see that this is also relevant for exchange between the troposphere and the stratosphere, right? Every once in a while you see a red blob coming out of the stratosphere going into the troposphere, and that gets mixed into the tropospheric surroundings. Or you have the reverse, where you have a blue blob or white blob going into the stratosphere, and that gets mixed in there.
What's the longevity of one of those blobs before they get mixed?
Most of the timescales here are going to be synoptic timescales, so 5 days, a week, roughly. That typical weather type of timescales. And maybe you can also say that the typical kind of spatial scales there along that black line spans an entire latitude circle, right, from left to right. So the typical scale there is wave 5 or 6 or something like that, meaning you can count 5 wave crests as you go along a latitude circle, or 6, so somewhere in that range, which I'll call medium scale. It's kind of where the dominant dynamics is. Okay. So eddies and the general circulation, after sort of this motivation for coordinates and dynamics along the tropopause. Eddies are obviously important for the general circulation, but this wasn't always realized. This is going back to the history, and the basic concept that eddies act to diffuse certain quasi-conservative quantities, such as potential temperature or potential vorticity, goes all the way back to G.I. Taylor, who introduced this, and he used these mixing length ideas that were around in the early 20th century. And he used this to explain transports of momentum and heat close to the Earth's surface, looking at some of the first balloon measurements, basically. But that was Harold Jeffreys, who was a mathematician who introduced this concept of turbulent large-scale angular momentum transport. He's essentially the first one to understand that in order to explain the wind structures across the planet, you need to have angular momentum transport between different latitude bands. In other words, that the fact that we have easterlies in the tropics, the trade winds, and we have westerlies in mid-latitude requires angular momentum transport. And he was the first one to really understand that, and they introduced this concept of turbulent exchange by the eddies. And then Albert de Font, Austrian oceanographer, scientist, introduced the same concept for temperature. It's where you may have heard this term Austausch coefficient, exchange coefficient, that he introduced. This is often used in the original German. I don't know why, but maybe it sounds fancy if you use it in English. It doesn't sound fancy to me, but anyway. Here's a quote from his paper that, as far as I know, only exists in German, but I loosely translated one of the sentences that I kind of liked, which is the idea that the mid-latitude flow can be regarded as pronounced grand-scale turbulence should not be viewed all too venturous. So let's venture into this idea. So in the free atmosphere, it's potential vorticity, as I already motivated, that gets mixed along isentropic surfaces. And that's because of both these quasi-conservative quantities, right? For adiabatic flows, this is what happens. The underlying assumption is usually that your eddy mixing length scales are small compared to the region that you have, which is not really fulfilled, but it's still there and it seems to work. And an important thing is that the turbulence is spatially inhomogeneous. And you can kind of see that in my animation that I showed. There was this waveguide, the black line along the tropopause, that was very wavy, and then there was other regions that were more turbulent away from that waveguide. And it's really that mixture of the turbulence away from waveguides and the waves along the waveguides that determine the system. And you really need to understand both. And there's no turbulence without waves and no waves without turbulence, that sort of thing. So here's, we're going through the history, Physics of Negative Viscosity Phenomena. This was a book by Victor Starr back in '68. I really like his depiction of how the momentum fluxes arise if you have a jet profile like this. So imagine this is a latitudinal jet profile, so strong here and weaker as you go away from it. And this is really all you need to know. And then you move through there and say you have a little departure to the north here. Because you're moving to slower background velocities, you're sort of stalling there, and then you're moving back to the jet, and now you're speeding up because you're moving into faster velocities, and then you get slower and faster again, and so on. So if you analyze that, what you find is if you go north, your v prime, your marginal velocity is positive, but the u prime is negative. You're going slower. And here you go faster, but you go into have negative v prime. So again, u prime, v prime is negatively correlated, and so on and so forth. It holds for the entire system. So just from that picture, you can understand why the momentum flux goes into the jet. It's like negative on this side, and it's positive on this side. And so when you analyze a momentum equation like this, you realize that if you write the momentum flux as sort of this flux gradient relationship, that the momentum fluxes go up the gradient of the background velocity, and then that's where that term negative viscosity came from. Oh, wait, I should use this. Related to that, this is sort of one of the little gems that you can sometimes find in the older literature. I found this whole question about the importance of the eddy momentum fluxes in the general circulation. All the way back, people just thought about grand scale meridional circulations driving the momentum balance. And then these eddy fluxes were introduced. And there was this exchange. Here's Rossby and Starr on the one side, and then they said that the momentum fluxes by the eddies are important. And they questioned that it's just the meridional circulations. And Eric Palmain, who was in Chicago at the same time, wrote a comment on that. And was very critical of this hypothesis that it's the eddy fluxes. And he said it's not clear whether the authors intended to question the necessity of meridional circulations. Such an intention would mean a complete change of the whole foundation of dynamic meteorology, and I doubt strongly that the genius of the authors recognized by all meteorologists will be sufficient for that goal. This is in the literature. And then there's this reply by Victor Starr. He goes into several of the criticisms. Apparently, Palmain suspects me of high heresy, lest I suggest that the energy production process may also be accomplished without the aid of meridional circulations. He goes on, and then I really like this final thing that he says. Any insistence at the present time that the fundamental facts concerning the mechanism of the general circulation have been established is unfounded and misleading. The history of science and all of our general experience in meteorological research points to the inherent danger of the premature acceptance of superficially plausible hypotheses as fact. I therefore maintain that under present circumstances we must encourage free experimentation with various hypotheses and proposals in order to see which ones lead to the discovery of new observationally verifiable facts, since definitive criteria for acceptance or rejection are lacking. It's just really great statements about how science ought to work. I just really love it. He couldn't have replied better to the criticism, I think. Okay. Just in case you haven't noticed, I'm a big fan of the history of science. I always try. There's a lot of these interesting things that you can find if you go back into the history. So anyway, here's eddy diffusion of potential vorticity. So if you write down the flux gradient relationship, then it formally looks like that. Your flux, meridional flux of PV, V prime, Q prime, would be given by minus some constant times the background gradient. And by that, it would be by definition down gradient. Now, if you couple this to the fact that the turbulence is inhomogeneous, then you can actually find that this leads to the generation of sharp features. And so all you need to do is assume that the eddy PV flux is spatially inhomogeneous like that. So here it's negative, assuming a positive background gradient, but then it goes to 0 here, and then it's negative again. If you then assume that you had a background PV linear with latitude like that, and you apply these PV fluxes, what they're going to do is they flux the PV down gradient on this side, and they flux the down gradient on this side, but they don't do anything right here. And in the end result, you get a sharpened gradient in the middle of the domain here, which becomes a jet, or a tropopause in my case. And all you had to do was flux PV down gradient, but in a spatially inhomogeneous way. So that's very important here. And that all the fluxes are down gradient, but there's 0 in the middle. So that's how really this happens. So let's look at this a little bit further. Why are these PV fluxes so important other than for describing the eddy mean flow interaction? If we look at the zonal momentum equation, this is written down here. This is in the quasi-geostrophic framework and transform Eulerian mean. That's not so important right now what that means. But you can write it down like this, where you have partial d by dt of u bar, the local tendency of the background zonal mean zonal flow. This is your Coriolis torque. And then it turns out that the PV fluxes represent the interaction of the eddies with the mean flow. If you have PV fluxes, you're going to change the mean flow. That's how they're importantly linked to the mean flow. So if I take this budget and I go to steady state, I get this balance. And if I throw in this flux gradient relationship, I get this balance, which has a really important result. Because what it shows me is that if I have a background PV gradient that's everywhere positive, as it is true in the atmosphere, in the interior atmosphere, then my circulation that's consistent with that has to be poleward everywhere. In other words, where F is positive in the northern hemisphere, V bar is positive, and where F is negative, V bar is negative. This explains the stratospheric circulation, actually. But in here, I just wanted to point out this important link to the zonal mean flow. More fundamentally, if you ask yourself, where does this really come from that these PV fluxes should be down gradient? If you go one order higher in the budget, so this is the PV variance budget, the budget for Q prime squared. If you write this down, then there's a term here that arises which is coupled to this PV flux. It's the PV flux times the background gradient, and there's higher order terms. If you neglect these higher order terms, this is dissipation, and then go to steady state, you get this kind of balance. So you get a balance between a production term from the PV fluxes on the left here and the dissipation, which is on the right. If you then assume that dissipation is truly dissipation, which means that it goes like something like minus alpha, a constant, times the perturbations. So it always dampens the perturbations that are there with alpha positive. And you throw that in there, you get this balance. And now in this case, the left-hand side is always positive, which means that the right-hand side has to be always positive. And that can only be the case if the PV flux is down gradient. So this is really fundamentally where that result comes from, that we think that this flux gradient relationship with down gradient eddy fluxes arises. So from that, you expect the PV fluxes to be down gradient everywhere. Okay, so let's look at this from a time evolution point of view. This is just a schematic of